It's my pleasure today to introduce Tristan Lecuyer, professor at the University of Wisconsin-Madison in the Center for, I had the acronym in my head, but it's CIMMS, right? Center for?
It's Cooperative Institute for Meteorological Satellite Studies.
Cooperative Institute for Meteorological Satellite Studies. Yes. So, Tristan hails from Halifax. He got his bachelor's and master's in physics at Dalhousie University. After thinking about doing a physics career for a while, he decided he saw the light and said, atmospheric science is where it's at. So he went to a great place to study atmospheric science, Colorado State University. And there he was quickly entrained into this amazing satellite mission called CloudSat, where he was really at the center of a lot of the algorithm development for retrieving many aspects of cloud properties from radars. And this was a spaceborne radar that flew around and gave us amazing data that many of us are still using, even as it's gone through many versions. So he did not stop there. He's been involved in lots of other mission development work, including the one that's going to be the focus of this colloquium. He directs this as a very large center, one of the largest atmospheric science programs probably in the world, it's a big effort to undertake, and I'm looking forward to his talk today. So he'll be focusing today on taking Earth's temperature, documenting the spectral character of Earth's emission. So please go ahead, Tristan. Yeah, welcome.
Okay. Yeah, thank you. I hadn't even thought about talking about my career path at all, but it is interesting that that I'm in a physics department here. And one of the things we've actually been trying to do a little bit at the University of Wisconsin, where we do have an actual dedicated atmospheric and oceanic sciences department, which is where I am, but is trying to actually engage a little bit better the physics department, and especially students that are interested in applied physics. I mean, I am still a physicist, and I consider myself to be an applied physicist. And as I was doing my master's in quantum mechanics at the time, and kind of wrestling with, well, that field, I was looking for an application to, maybe branch out into one that would, potentially have job opportunities. And I encountered a professor named Chong Fu, who's now at the University of Washington, took an atmospheric radiation class there, which is all quantum mechanics, basically. It's looking at, the rotation and vibration spectra of various atmospheric molecules. And basically just asked him, how do I get into this field? And he suggested 2 or 3 professors that I may want to get in touch with. I got in touch with my advisor, I guess soon to be advisor at Colorado State University at the time. He was very excited to bring me on as a grad student, and the rest is kind of history. But so just for those of you who are considering career pathways, I guess that will be my short lecture, that there are a lot of different applications out there that kind of leverage the physics background that you're getting from here. Now today, and so I really appreciate also your introduction, the CloudSat project that I worked on with my advisor, Graham Stevens, formed about the first 20 years of my career. It was a very successful mission. I was very lucky in that regard. I have had a few other projects since then, and this is sort of the next big phase of my career. This I'm going to talk about today, an Earth Venture satellite mission that I'm leading through that NASA program, where we're planning to launch 2 CubeSats, hopefully in about a year's time. It's taken about 6 years to get here from the proposal stage. So we're actually quite excited that we've gotten through a lot of those hurdles. And I'm going to talk a little bit about some of the background science, try to sort of introduce you to why we need these measurements, and why they're particularly useful for understanding Arctic climate. And then I'm going to talk a little bit about what I think is really exciting about the mission, the fact that we are going to be using these fairly small, relatively, I'll use the word relatively inexpensive platforms. When people hear $40 million, they don't think of that as being cheap, but it is very inexpensive compared to some of the bigger satellite missions that cost over $1 billion. And so we think that this is an opportunity to collect science quality, research quality data using a platform that we can afford to fly many of these and actually potentially address a lot of science questions we haven't been able to address so far. So that's a lot of time on my introductory slide. Let me get into the actual talk itself. So I'm going to start by really taking a step back and kind of talking about a physical process that is relatively well understood and something that you're probably all familiar with, even outside of strictly an atmospheric science community. That is this process of Arctic amplification. Living in Canada, you should be aware that Canada itself and Scandinavia and a lot of the northern countries are warming faster than other areas of the Earth. The mechanism, or at least the very simple version of the mechanism why this is occurring, is related to sea ice and what's happening in the Arctic to the sea ice cover. So very simply, as the climate warms, sea ice is melting. It's not completely going away. It just means that it's receding earlier in the year than it normally does and receding further away to a lower minimum in September than it used to. As that happens, because sea ice is much more reflective than the ocean, and I'll show an example of this in just a second, you absorb considerably more shortwave radiation from the sun, especially during the summer months, and that allows the ocean itself to warm up, and that's a feedback process then by which you melt more ice and so on, amplifying the temperature increases you get in the Arctic. This is something that's been around for a long time. Like I said, this is almost, I would consider, common knowledge, at least among scientists at this point. This is a result, one of the earliest climate models. It was a sort of a one-dimensional, this is latitude on the x-axis and temperature on the y-axis by Budico in 1969, where he had a simple model that once the temperature got, at a given latitude band, got colder than a certain temperature, he would basically trigger the formation of ice and change the albedo in the model to ice. You would iteratively solve this model then. The ice would grow and shrink as a function of latitude until it reached an equilibrium state. And what he basically did was ran a simulation where he had sort of this model tuned to freeze into ice when the temperature reached, I think it was -10°C, and then another model where he did not allow the ocean to freeze at all. And you see that at the higher latitudes, he got this fairly significant increase in temperature of about 10 degrees. Whereas in the equatorial regions, he got about 2 or 3 degrees temperature change. This is exactly the process of Arctic amplification, and this is 1969, already being sort of simulated relatively accurately. So here's the process that we're talking about. When you look at the computer screen here, especially, you can see this right away. This is obviously a very bright scene. This is early in the year, probably April in the Kara Sea. You have a lot of ice cover here, and this is what it looks like later in the year in June when a lot of the ice has gone away. This is obviously not climate change or climate evolving. This is just simply seeing how dark the ocean actually looks, relative to the ice covered surface. And so you can see that process, that if this transition were to occur earlier in the year or were to cover a larger expanse of the Arctic, we would absorb a lot more shortwave radiation and we would warm up the Arctic. So that's just a visualization of what is going on. The question, I guess, is, can we now observe this process actually taking place in our climate? Really, the only way we're able to measure anything in the Arctic across the entire Arctic is using satellites. So I'm also a satellite person, so I will show you the satellite perspective on this. Here, what we have is the absorbed shortwave radiation. So this is taking what we calculate for the incoming solar radiation at the top of the atmosphere and subtracting what we see reflected back to space. And we're measuring that reflected back to space with an instrument called CERES, which has been around since 2002. Cloud in the Earth Radiant Energy System, I think is the acronym. And so in clear skies, you see that this is with no clouds present, any scene with no clouds present. This is how much energy anywhere, any given place in the Arctic is absorbing on average over the last 20 years. When there's clouds present, what you see is clouds are obviously reflective in their own right. They block some of the radiation from getting to the ground, and we absorb a little bit less radiation in the cloudy sky conditions. But whichever one of these you look at, it's easier probably to look at the clear sky. You can immediately see that areas that tend to be more open ocean for a longer time of year around the periphery here of the Arctic sea ice, they tend to absorb more shortwave radiation than the areas that are covered in ice, and of course Greenland being the one that really stands out as being an ice sheet all year round and reflecting a lot of radiation. So the question is this changing? And this is some work that I did with a PhD student who graduated a couple of years ago, Anne Sled. She actually took the average of every month of series observations since the start of the mission in 2002, did a weighted average of the absorbed shortwave radiation over this entire region. She separated out ocean areas because those are covered in ice from land areas that get covered by seasonal snow. She also separated out the clear sky and the all sky. All sky just meaning every scene you see, clear sky meaning only when there's no clouds present. And this is the time series. In any one of those types of conditions that you can imagine from 2000 to 2020, you see that there is a statistically significant increase in the amount of shortwave radiation being absorbed in the Arctic. So this was one of the first papers that's shown that just in the short satellite record, in a 20-year satellite record, we're actually able to observe this process of what we would call Arctic amplification, or at least the increase in the absorption of shortwave radiation in the Arctic. And just in case you're interested in what this looks like spatially, again, I'll come back to the point where you typically see the largest changes. This is now the change in, over that 20-year mission, the change in absorbed shortwave radiation for each of these grid boxes in the Arctic. And you see that most of the change is occurring on the edges of the perennial ice. So associated with ice basically being melted off earlier in the year than it was back in 2002. Again, this is only 20-year trend, but you do see significant area here where the absorbed shortwave radiation has been increasing, and it's typically increasing the fastest where the sea ice loss is the greatest nowadays. Not only that, to kind of close the loop here, if you actually look at observations of Arctic temperature, this is what I've already said. I think we're all aware of this now. This is the GISS surface temperature record, averaged globally from 1880 to present day, and just the Arctic mean temperature from 1880 to present day. And you see that the temperatures have been increasing in the Arctic about 3 times as fast as they are anywhere else on the Earth. I think somebody mentioned over lunch today that in Canada, they're increasing at about twice the global rate. I think the same is true of Finland. So we do see evidence of this Arctic amplification. It's not just absorbed shortwave radiation. It is being translated into heat, and the Arctic is warming faster than the rest of the Earth. Also, maybe more alarming than that, because maybe a 2-degree temperature change is not something that excites a lot of people, maybe more so scientists and the general public. But this is a pretty alarming plot. This shows data from another mission called the Gravity Recovery and Climate Experiment. Basically, it consists of 2 satellites that fly in formation with one another. And by measuring the distance and small changes in the distance between the 2 satellites, they're actually able to estimate the mass of basically the Earth that they're looking at below. It's small changes in gravity affect the distance. What they've shown is that since 2002, when they launched, and actually there's a bit here of a extended mission, a second mission, the Grace follow-on that launched in 2018. You see a significant loss of mass of the Greenland ice sheet, on the order of 250 or so gigatons of loss per year. So we are melting tremendous amounts of water off the Greenland ice sheet, which is going into the oceans and is causing the ocean to rise. And so this is something that should be alarming to everybody, and one of the reasons we really want to understand how quickly mass is going to come off of the ice sheet in the future and increase global sea level. So to pick up on that point then, how well do we actually measure these observed changes in the Arctic? And this is kind of where the story is going to get a little, let's call it less certain. As you're probably all aware, I mean, all climate models do predict, obviously, that the planet is going to warm. Most, I think all climate models also predict that the Arctic is going to warm faster than everywhere else on the Earth. But when you look at specific impacts of that warming, something like, for example, trying to project sea ice extent into the future out to 2100, let's say to a time period where carbon dioxide might be 50% more than it is today, what you see is that there's actually this huge envelope of different simulations by state-of-the-art climate models across the world. There's about 30 research centers right now that run climate models. that produce these kind of predictions. And you can see there's just an enormous variation, with some models saying that sea ice is going to almost vanish by 2050, and then others that say it'll plateau and remain relatively steady, by around 2040. So there's this really large range of extent of sea ice. If you then also look at something like the air temperature above Greenland, this is now two different scenarios. There's actually multiple scenarios on here too. It's harder to see because all of the envelopes overlap. But if you focus here on two of the scenarios, the blue scenario here is if we make drastic changes in the amount of emissions that we're putting out right now and basically level off the carbon dioxide concentration to where it is today. That's the blue curve. The red curve here is if it's sort of business as usual and countries continue to produce about what they're producing now in terms of carbon dioxide. This is what happens to the air temperature above Greenland. The solid curve here represents the model ensemble mean, the average of all the models. All the squiggly lines here represent those individual models again and their different predictions. And you should be able to see that there's, again, a wide spread, something like a factor of 4 spread between different climate models scenarios on what the 2-meter air temperature is going to be over Greenland. And of course, temperature plays a big role in sort of how much Greenland's going to melt. So it's kind of important that we get this right. Here's one particular model. This is the community Earth system model that NCAR produces in Boulder. This is a graph from a colleague, Jen Kay, several years ago. But she actually compared the temperatures in the community Earth system model with observations, these little circles that were actually ground-based automatic weather station observations. And what she found is that the model was biased by about 2 to 3 degrees too cold over most of Greenland, especially in the melt season in the summertime. And this is another study by a colleague of her also in Boulder at Jan Leenaerts, who showed, not too surprisingly, because the models are too cold, they actually underestimated. So I just showed you this solid red curve. This is the GRACE measurement of the mass loss on Greenland. These little dash curves are the predicted melt losses for the business as usual scenario simulated by the ensemble of climate models. And you can see that they're actually all underestimating how much mass loss the Greenland ice sheet is actually suffering today. And so then the question is, how do you trust the predictions into the future if we have these underestimates today? So I guess the answer to my question is maybe not as well as we would like. There's consistency in the trends of all of these predictions, but there's a huge amount of spread between the different climate models. And we'd really like to try to reduce that spread a little bit. And I'll come back to this diagram. So if this process of Arctic amplification is so simple, why is it that we have so much uncertainty across the climate models? And obviously the answer is that this is not nearly as simple as I've been kind of making it out to be. As you warm the Arctic, many other things change. The amount of water vapor in the atmosphere changes. The lapse rate in the atmosphere, the rate at which the temperature decreases with height changes. The amount of clouds may change. The brightness of the various ice surfaces may change. And what we're looking at here is actually a really good paper in Nature Geoscience in 2014 by Pithen and Moritzen, who looked at the contribution of all of these changes across all of those different climate models to the warming in the Arctic. And you can see, again, this is where the spread is coming from. It's the different models, even where they all predict the same sign, that the albedo is, this is the brightness of the surface. It's all going to increase, but there's a huge range of the different predictions among the models as to how much. Likewise, how changes in clouds, this is actually one of those that could be either positive or negative, depending on which model you look at. There's quite a huge spread in how the different models treat cloud changes and what that contribution is to Arctic warming. So I just highlighted those two in particular because I'll show an example of why things are just not as simple as I said. Here's another example, springtime sea ice. I think this is north of Alaska. So now this is the, the corresponding version when the sea ice has gone away. There's almost no sea ice in this diagram, but now instead there's actual cloud cover, and you can see that the effects of removing the ice are significantly diminished when there's a cloud present relative to the previous example where there was no cloud present. So this already talks about the complexity. If there are clouds present, you can't simply draw the conclusion that by reducing sea ice, you're going to absorb more shortwave radiation. You really need clear skies in order for that to happen. Just one example of the complexity and the interplay between the albedo of the surface compared to the albedo of the clouds. All right, and so now I'm going to fill in the rest of this plot. I showed you the left-hand side already. This is the trend in absorbed shortwave radiation for clear skies, cloud-free skies. This is what the true change in absorbed shortwave radiation has been since the 2002, since the beginning of that series climate record. And what you can see is that it's not nearly as much as it would have been if it was just a simple sea ice problem. The clouds have reduced significantly the amount of increase of shortwave radiation. You still have increases over a lot of the area, but the reduction, there's a significant reduction. I bring all of this up mainly to just say that it is really important that we not only measure sea ice and try to infer from that what's happening in the Arctic, but that we also measure all these confounding factors like clouds, water vapor, and other changes in the Arctic in order to be able to predict what the net effect of the climate change is going to be. Okay, so that's a very Arctic focused message so far. I do want to convey to you and make sure that you realize, I've already sort of hinted at the melting of Greenland, but that what happens in the Arctic does not stay in the Arctic. It's actually very important for the entire globe. And so I'm going to step back and just look at the Arctic energy budget. This is the balance of incoming shortwave radiation. We've talked a lot about this. This is what increases when sea ice is melted and you go to a darker surface. Well, the way the climate works is that is offset by, and in fact, in the Arctic, it's actually dominated by emitted thermal radiation. Any object, as you know, that has a certain temperature emits radiation to space. And so what you see is that the Arctic receives about 80 watts per square meter on an annual average of incoming solar radiation, but it emits about 200 watts per square meter of thermal radiation. And the way this balances, I mean, if this was the only thing going on, the Arctic would rapidly cool and we would, basically be it would just be an ice block all year round. But what happens is, to balance this off, the lower latitudes, which receive more sunlight, transport a lot of energy through weather systems around the planet into the Arctic to kind of keep things in an approximate balance. So through this mechanism, this balance between incoming shortwave radiation and outgoing longwave radiation actually impacts the weather systems around the whole planet. And so here's a diagram that is kind of meant to convey that in a little bit more explicit detail. So now we have the globe. We actually have the energy budget, the same numbers I just showed you. And for a good reason, I'm not going through all the numbers. There's no sense in doing that right now. The main message is that there's this heat transport. But basically, if you look at the numbers in the northern hemisphere and in the southern hemisphere, you see these dramatic deficits of energy due to the emitted radiation at both poles. And that drives this transport of energy from the tropics that receive a lot more sunlight toward the poles. In both cases, it's about 1.2 petawatts or so of energy, 1.2 times 10 to the 15 watts, so a tremendous amount of energy. And again, we won't go into the details of how this works, but what that does is it drives the atmospheric circulations that we all live in and experience. In the tropics, it drives a thermal overturning circulation where air near the equator rises and then subsides in the kind of mid-latitudes around 30, 35 degrees north and south. And then in the mid-latitudes where we live, the atmosphere is kind of stirred by these weather systems that rotate counterclockwise and advect warm air from lower latitudes on the eastern flank toward the North Pole, and then drag colder polar air down toward the lower latitudes on the western side. And so you have these circulation patterns. This is our weather. This is what we're probably about to experience tomorrow here, another extratropical cyclone. This is the tropical weather pattern. This is basically what brings the excess heat from the tropics up toward the poles. So the message here is that that deficit of energy and any change in that deficit of energy actually changes the weather patterns around the whole world. Okay, the other part of the message, and the reason this is titled Uncertainties, is I have not pointed out yet that there are error bars on some of these numbers. If you focus again mostly on the thermal part of this diagram, what you notice is that there's errors of about, let's say, plus or minus 10 watts per square meter on this energy exchange, this emitted energy. This is the sort of upward emitted energy from the ground to the atmosphere, and the downward emitted energy, or the greenhouse effect, from the atmosphere down to the ground. Both of them, from observations, we think are accurate to about 10 watts per square meter. If instead of observations you try to use models, you actually find that the error bars are similar, maybe even a little larger. If you look at weather models, this number ranges by about 20 watts, 22 watts per square meter. This is the greenhouse effect. In climate models, it actually varies by about 32 watts per square meter across the climate models I've shown so far. And the emitted from the surface to the atmosphere also has about a 20 watt per square meter error bar in weather models. These are reanalyses. If you are an atmospheric scientist, you know what that is. Climate models show about a 30 watt per square meter bias, range spread in the emitted long wave radiation from the surface. So we have an enormous amount of uncertainty. I'll show you exactly how important that is in just a second. But there's a lot of uncertainty in how well we can constrain these numbers. And my argument is basically that a lot of the variation that we see in the Greenland temperatures and in the amount, the estimates of the amount of runoff you get from Greenland, in the sea ice loss, a lot of that uncertainty is coming from the fact that we have this amount of variation in these numbers. Here's one example. I just said that the amount of heat transported from the lower latitudes to the poles is really kind of what dictates the weather systems around the planet. Well, you can actually calculate that. You can look at what the deficit of energy is in the Arctic, and that's what this is here. Now as a function of the different times of year. So this is calculated for each month. And what I'm showing here in the envelopes is the spread between the different climate models of this estimated heat transport into the polar regions. And so you see on the y-axis here, we have the heat transport in petawatts from -1 watt per square meter up to 1.5 watts per square meter. And you see there's an annual, there's an annual cycle of this number. Depending on whether the sun is up or not, a very strong annual cycle. But the main message, and of course all the models get that annual cycle correct, but what you see is that especially in the summertime, there is about a factor of 3 spread in the estimate of how much heat needs to be transported into the Arctic between the different sources of observations. And so, excuse me, I'm losing my voice a little here. And so again, this error bar, this yellow, the way to interpret this yellow is this is a spread in the amount of weather systems and the amount of heat transport that they're transporting from across the different models. This has huge implications for trying to infer how, let's say, precipitation might change in a warming climate, or how frequent we may get storms in a warming climate. If models don't agree on how much heat needs to be transported, they're not going to agree on what the weather systems are going to look like that do the heat transport. As another source of uncertainty, I just want to go into that last implication again. This is just to again convey how important the Arctic region is for everybody on the Earth. I mentioned already that the melting of water from the Greenland ice sheet is actually raising sea level. We did do some simulations just to show how important a 10 watt per square meter error is on the various processes that govern the evolution of the ice sheet. Without going into the details here, this would be more interesting for somebody who actually models ice sheet dynamics. But basically what we did was to take a very sophisticated model of how the ice sheet evolves. And we actually ran 2 different experiments, one where we drove the model with a certain observational set of radiation coming down onto the ice sheet, and then another where we just added 10 watts per square meter to it just to see what would happen to the ice sheet. And what you're looking at over here for each of these 3 locations, one in the northeast, one in the southeast, and one over on the west, you're looking at the simulated temperature of the ice sheet between the control run, where we, like I said, just used the best observations we had of the radiation, and then the those same radiation numbers, but augmented by 10 watts per square meter, representing the maximum the error bar would suggest could happen. And you see that you get at least maybe 2 or 3 degrees of temperature difference, depending on where you are. But actually, more importantly, you get about 10% more runoff at all 3 of these different locations. So this is the labeled surface mass, but basically what this is the amount of mass the Greenland ice sheet is losing under these 2 scenarios. You get a 10% change in the mass loss when you add 10 watts per square meter. So this is basically just to convey to you how important it is that we nail this number down. A 10% change in mass loss could mean, the difference of several inches of sea level rise in a 100-year simulation. This generalizes those results even more. I did mention, so the observations are probably within plus or minus 10 watts per square meter. Climate models are actually even less certain than that. So what we did was ran the same ice sheet model, but we're up to 20 watt per square meter additional radiation into the surface, or a 20 watt per square meter less radiation into the surface. And if you just focus on the solid blue lines here, this just shows the difference in, again, runoff or mass balance change in gigatons per year from the ice sheet under these different scenarios. You see it's more or less linear. It doesn't have to be linear. It just turns out that way, that you get about maybe 7 or so gigatons per year more runoff from the ice sheet when you add 20 watts per square meter. Thank you. And you get about 7 watts per square meter less if we had 20 watts per meter less surface radiation going into the ice sheet. This makes an enormous difference when you're trying to simulate the impacts of climate change on global sea level. So we know that one of the biggest impacts right now of climate change is this rising sea level, the fact that tides are starting to inundate coastal cities around the world, the fact that storm surges from tropical storm systems are getting higher because the sea level is higher to begin with. It's having a greater impact. Whether or not you have an extra 14 gigatons of water going into the ocean per year makes a big difference in assessing the impacts of these climate changes. So, okay, this is just a summary slide to kind of summarize the sort of lessons so far. Basically, all of that was to convey to you that it is really important that we understand the radiative fluxes, the exchanges of energy between the surface and the atmosphere, and I guess out to space in the polar regions, and especially in the Arctic, because of the fact that it's this deficit of energy and this corresponding surplus of energy in the tropics that really leads to the weather circulations around the planet and also drives the amount of runoff you get from the ice sheet. So now we come back to this diagram. How do we actually reduce the uncertainties on this diagram? And in particular, I've sort of been focusing over here now on the emission side of the diagram. If you notice again, that even though the focus, let's say, of a lot of Arctic research and Arctic amplification is on what's happening to the shortwave side, it turns out there's only 82 watts of shortwave energy coming into the polar regions. There's 196 watts of thermal energy going out. Maybe the most important thing for us to nail down is actually the thermal part, the emission part of the spectrum here. And that's basically where my satellite mission is sort of focusing its attention. And in particular, what we want to be able to do is measure the entire spectrum of emitted radiation from the polar regions. So one of the sources of uncertainty, that at least we believe, is the fact that so far, all of our current satellite sensors only measure spectral radiation. This is like resolving the actual, this is just basically a Planck function. You probably recognize this. These are Planck functions for the whole world, averaged over the whole year, for the Arctic in September, which is kind of the warmest a polar region ever gets, and for the Antarctic in September, which is the coldest the Earth ever gets. What you're seeing is some of the little absorption features by the atmosphere, but basically these are Planck curves. So far, what we've measured systematically around the globe using satellites is only radiation up to about 15 microns. And if you look at this curve, plotted in this sort of wave number domain, you can see that that represents about half of the global emission. It actually represents less than that if you go to colder areas because the Planck function shifts to longer wavelengths. It only represents about 40% or so. So the number in parentheses is actually how much you miss from the wavelengths we haven't measured yet. And so you can see like 60% of the energy is in these wavelengths longer than 15 microns in Antarctica in September. This actually shows a map if you're interested in kind of what the distribution of this looks like. So this is the fraction of energy that lies at these longer wavelengths greater than 15 microns that we've never systematically measured as a function of anywhere on the globe you want to go. And of course, the colder you are, like I said, because the Planck function shifts to longer wavelengths, the more energy it is that we haven't actually detected. We argue that this 50% or so of the global emission carries a lot of information that we could be using to start to constrain polar climate processes. For one thing, this upper panel here shows theoretical curves. These are laboratory type experiments showing what the emissivity, this is just sort of the fraction relative to a black body that gets emitted as a function of wavelength for various surface types. It shows significant variation in the emissivity of various surface types, including things like looking from ice, which is the orange curve, to water, which is the cyan curve here. That would be the transition that we've just talked about, going from sea ice in orange to open water in cyan. There's a tremendous amount of variation, at least theoretically or in the laboratory, that we have yet to be able to actually document in this surface emissivity. And a 1% change in emissivity means a 2 watt per square meter change in the amount of emitted radiation. Here you have differences on the order of 4 or 5% that can easily give you the 10 watts per square meter uncertainty I just mentioned. Likewise, and that one's very easy to kind of see mathematically where the error comes in. It's a little harder here, but the atmospheric greenhouse effect, that's the other term. That's the atmosphere trapping the radiation before it gets out to space and emitting it back to the surface. This is extremely sensitive to things like thin clouds and small, low water vapor amounts that are very difficult to observe in these wavelengths less than 15 microns, where all of our today's sensors operate. But the far infrared is in the rotation band of the water vapor molecule. There's extremely strong infrared signatures of very low water vapor concentrations. And so we expect to be able to, by filling in that far infrared gap that we have not yet observed, be able to detect the greenhouse effect from very low water vapor concentrations over Greenland that could play a big role in how much Greenland is melting and how the temperature is varying on Greenland. Here's one example of, this will be the last result I'll actually show before kind of getting into talking just a little bit about the mission itself. This is a work from a collaborator a few years ago, Zhenglei Huang. He's a member of our science team. All he did was he took a very good climate model. This is the CAM5, the NCAR model, the previous generation of the atmospheric model. And he actually ran simulations where he used their assumptions for surface emissivity, and then those laboratory measurements or simulations that I showed on the previous slide. He basically just swapped out what they were currently doing, which was actually I think it was a constant number across the whole spectrum, with those spectral variations I just showed through the far IR. And what he was able to show is that this is the temperature response, the difference in temperature between those two simulations. Notice that you get differences of up to 3 Kelvin, even in just simulating today's climate. This isn't climate change, this is just simulating the present day. He was able to show sea ice, and actually it's not too surprising that those are kind of related. The temperature is warmer where the sea ice fraction actually experienced major changes by just changing that surface emissivity. Notice there's also areas where sea ice actually increases. That's sort of evidence that the whole circulation pattern around the Arctic was sensitive to this surface emissivity assumption. And actually more evidence of that is this is how snowfall predicted by the model changed when all he did was change the emissivity of the surface to be something that he felt was more realistic. And you can actually see the pattern of snowfall around the Arctic changes in a response. So these climate models are hugely sensitive to these assumptions, and we've never systematically been able to actually measure them. Okay, so that does bring us to, I think actually I'm pretty good time here. That brings us to the satellite mission itself. The reason I spend a lot of time showing results that look like they're preparatory to the mission is because we're not launching for another year. So that's what we've been working on so far. But basically, this polar radiant energy in the far infrared experiment, or PREFIRE, is going to try to fill, at least to some extent, this far infrared observing gap. We're actually going to try to measure spectral fluxes from 5 microns all the way out to 54 microns. That covers about 97% of the Planck emission curve for the Earth, as opposed to less than, which is what we currently measure. I will put a caveat out there right now. I mean, we're going to do this with CubeSats. It's a relatively inexpensive mission. So we're not going to be doing this at the same spectral resolution as current sensors are in the mid-infrared. That those hyperspectral instruments right now have 8,000 channels that just go up to 15 microns. We're only going to have 64 channels that go up to 54 microns. So we're measuring at a spectral resolution of about 0.84 microns. But the point is, we are filling in this gap in the observing system that we just don't have yet today. So here are today's sort of state-of-the-art measurements. We do have one series broadband measurement that measures a single measurement that integrates across the entire spectrum, but PREFIRE is going to try to break that down spectrally and use that information to really understand how the emission is varying in the Arctic, to try to nail down some of the uncertainty that we have in that thermal flux part of the Arctic energy budget. This is kind of the mission in one slide summary. So this is already a little bit out of date here. If you ever want to talk offline, I can talk to you about the joy of trying to run a satellite program during a pandemic and other things that we've been dealing with lately. So we are delayed about a year from where we were anticipating to launch. Like I said, even this slide is kind of a little bit out of date. But the idea is that we're a one-year mission nominally. We hope that even these CubeSats will last at least 3 years. So we're hoping we'll get more data, like almost every mission that's successfully flown has seemed to have done. But we are going to fly these two 6U CubeSats. 1U of a CubeSat is 10 by 10 by 10 centimeters. So we are 6 of those sort of stacked in a kind of a cereal box shape, I guess, formation. Each of the CubeSats is going to fly between 510 and 540 kilometers above the Earth with an inclination of 82 degrees. That's the sun synchronous orbit. And the idea behind flying 2 CubeSats is that with 1 CubeSat, we can measure what the emission spectrum of the Earth looks like, and especially in the polar regions. But with 2 flying in different orbits, we'll get these intersections separated by between 1 and 12 hours, where we can actually see what the process of, let's say, melting the ice sheet does to impact the emission spectrum of that region. So we're hoping to do time differences between the 2 CubeSats to really understand what processes are affecting the emission, not just to document the emission. What's exciting, or really exciting to me about this, again, is that we're able to make this very novel measurement, something that hasn't been measured before, using this CubeSat platform, which is quite inexpensive. The 2 CubeSats themselves only cost about $6 million total. In order to do that, we had to be able to minimize a lot of the instrument hardware and get it to fit in a sort of 2/3 or so of this box. This is the Jet Propulsion Laboratory, and a lot of the great work that they do to achieve sort of new technology. Some of this comes from a moon mapping mission technology, and then some of it comes from some of their work on Mars. But in the end, we have an instrument that weighs less than 3 kilograms, on average uses about 4.5 watts of power. You can kind of imagine, I don't know what this laser is, but it's probably milliwatts. But anyway, it's less wattage than some of these light bulbs around. And we're going to be able to measure 64 channels worth of data using this little CubeSat platform. The main technological advances that allowed this are these advances in these CubeSat systems, which is just amazing right now. I mean, they're able to run the power subsystem, the attitude control, command and data handling, basically the radio, and also even transmit the data that we're collecting down to Earth from less than 1U of space, so less than 10 by 10 by 10 centimeter cube. The solar panels are extremely efficient now, and they're able to power this whole thing so that we're able to actually collect data globally, even when we're on the dark side of the orbit. And then there's these advances in the thermal imaging capability. The biggest one probably being these ambient temperature detectors, which are now able to measure low energy photons all the way out into the far infrared. This has always been a hang up and why we haven't been able to do this in the past. It's because you've had to cool the detector, and actually trying to cool a detector and then launch it into space is something that's prohibitively expensive. But also we have new optical techniques and other developments that have allowed this instrument to be reduced down to such a small size. There's some out-of-date figures on here. That should be 3 kilograms. So with this instrument, this is what we're going to be able to measure. This is a high-resolution spectrum. This sort of soft blue line. Our channels, like I said, are not going to be super high spectral resolution. Those are the squares. But we are going to be able to cover the entire spectrum from 5 microns out to 54 microns. This is now plotted in, I think I didn't show, yes, this is actually incorrect. This should say brightness temperature. So what we actually did was convert the radiances that we're going to observe. This is the Planck function you may be used to seeing, to a brightness temperature. And so the title of my talk, to come back to that, we're basically going to be measuring the temperature of the planet at 64 channels out to 54 microns. And these little variations in that temperature are what's going to tell us about what's in the atmosphere and what the characteristics of the surface are. So measuring the complete spectrum, basically we're going to go from the current picture that we have of the polar climate, which might be a fingerprint that looks something like this, to hopefully filling in the fingerprint a little bit more by getting those extra far infrared channels that are sensitive to water vapor, thin clouds, surface emissivity, things we don't know very well right now. This is an example. I'll go through this relatively quickly, but again, from the same colleague, Zhanglei Huang, what he was basically doing was showing how the relative humidity feedback in the CMIP5 models, these are the climate models from the last generation, basically how that radiation, or gosh, I don't know why, too many words there are, how the relative humidity feedback looks in different portions of the spectrum. This is how the outgoing long wave radiation as a whole looks with respect to this relative humidity feedback. This is what the relative humidity feedback looks like just in the long sort of far infrared channels between 30 and 100 microns. This is what it looks like in the window, this dirty window region from 16 to 25 microns, where the atmosphere does have a little bit of absorption, but not a lot, so it's called a window. And then this is the mid-infrared window, which is a cleaner window, has very, very little absorption from the atmosphere. And the main point here, I'm not going to go into the details of why these look the way they do, because that's a lecture on its own, is that you have a different signature in the longer wavelengths, the middle wavelengths, and then the ones that we measure today. And from this difference between these 3 different types of wavelengths, we expect to understand a lot better how this relative humidity feedback is actually operating in current climate. Let's see, where am I at in time here? I'm getting pretty close. So let me go ahead and I just want to talk about some of the preparatory work we've done in developing some of the algorithms, just so you can kind of see what kind of products we're doing. And it may be of interest to you to know the types of techniques we're using. So this is one algorithm that's going to essentially just mask where we think clouds are occurring. We think we're going to have great sensitivity to very thin clouds using this instrument. And so this is a PhD student of mine, just starting PhD student. He just finished his master's, who is developed this neural network-based cloud mask to use the full spectrum, all 64 channels, and basically trained using simulated data from a global climate model, or say actually global high-resolution cloud model. He's developed this algorithm to estimate where it's cloudy, where it's not, and with what kind of certainty. And so this is an example of his algorithm. This is actually the truth for, again, a full Arctic scene of cloud cover. And this is how his algorithm performs, with the red being confident clear. That corresponds to the black up here in the truth. And then the blue being the confident cloudy regions. You can see they line up very well with where things are white in the upper panel. He thinks he can achieve an accuracy of about 94% in terms of cloud detection. This varies with the height of the cloud and the water content of the cloud. I don't think I need to get into that. As far as water vapor is concerned, like some of the other hyperspectral mid-infrared instruments out there, try to retrieve properties of, profiles of relative humidity and temperature throughout the atmosphere. most interesting on this slide. It's basically showing the sensitivity of each of our wavelengths. This is from, again, 5 microns out to, actually this one stops at 35. We go out a little further than this, to changes in water vapor at different heights in the atmosphere. And so what you can see is, even if you just look at this far infrared portion from 15 microns onward, we have sensitivity to the mid and the low portion of the atmosphere. And as you go to further out to longer and longer wavelengths, our sensitivity basically transitions to higher and higher in the atmosphere. And so it's this change in sensitivity across these wavelengths that's going to give us the ability to retrieve full profiles of temperature and humidity, even in the really dry Arctic regions. This is something that current instruments have trouble doing. This is our surface emissivity product. I don't need to go into the details of it again, just to say this is a big step forward to hopefully advance our understanding of how different surfaces emit radiation into the atmosphere. And again, these are all wavelengths that have not been measured before. So we have a product that's going to actually measure that and supply it to climate modeling groups. And then likewise, we're going to try to, in cloudy skies, try to use the fact that our different wavelengths have different sensitivities to the phase of the cloud, the size of the particles within the cloud, the height of the cloud, the thickness of the cloud, to try to retrieve all of these cloud properties in, again, these cold, dry climates where current sensors really struggle to retrieve these different cloud properties. And this will hopefully improve our understanding of this interplay between the changes in the surface albedo and the changes in the atmospheric albedo due to clouds. Spectral flux product. Okay, I'll end on this note. This is my next to last slide. One thing that we are very proud of with the PREFIRE project, and I was just mentioning this in the coffee break beforehand, is we have direct input into our satellite mission from modeling groups, both process modeling groups. So this ice sheet model that I was showing, one of our collaborators runs that model, is intimately involved in the development of the next generation of that model, and also climate modeling groups that are basically using that process model as well as many others to simulate the full climate. And so they have been giving us input into what kind of data they would like to see and how we can best shape the data to directly have an impact on their model. And so we have like I said, two members of the team that are going to take the observations, directly improve models, not just by sort of throwing models over and saying, hey, use it to verify your model, but we have actually a pathway through simulators to include the data that we collect in the ice sheet models and climate models, and then rerun some of the climate model simulations and see if we can reduce some of this uncertainty in the projected pathway of future climate. That comes both to how much mass is coming off the ice sheet, as well as what the actual temperature in the Arctic and around the globe will look like in the future. Oh, sorry, this is the second to last slide. This is just to show you that we have an actual, so that sounds all very theoretical. We actually have hardware now. This is super exciting. This is pictures from Blue Canyon Technologies in Colorado. This shows our CubeSat all folded up. This is how it's going to look when it's on the rocket before it launches. And again, the dimensions here are 10 centimeters depth, 20 centimeters wide, and about 30 centimeters or so kind of into the page here. This is it sort of sitting on its side with the solar panels unfurled. It's a total of about 1.4 meters across, even with the solar panels opened up. But the point is, we actually have built the thing, actually two of them. They're both in environmental testing right now, and we're expecting to kind of put them in storage and try to go find somebody to launch us here in the next month or so. All right, there's a summary. I think I'll just hit on a couple of the points here. Again, by observing these radiances across the full spectrum, well, first of all, I think it's interesting just to know what the emission spectrum of the whole planet looks like. We have these theoretical calculations of what it should look like. We've never really measured it. I think just that will be an achievement. But from that, hopefully we'll be able to derive these surface properties, water vapor in the atmosphere, temperature perturbations in the atmosphere, and cloud properties that'll help us to evaluate and ultimately improve models. And then again, I'll emphasize this fact that we actually do have modelers on the team who, as soon as we collect the observations, will hope to try to revise their climate models and actually do a new projections of future climate and see how things evolve. So I think with that, I'll stop and take some questions.